Geomorphology is, at a rather fundamental level, the movement of material and mass around in landscapes. We can think about geomorphology in terms of the source to sink concept, where sediments are produced in upland areas by processes like weathering or the erosion of rock by lots of different processes, wind, water, ice, etc. That material is then left on hill slopes. It is then carried by mass movements, things like landslides, down into the fluvial system, and then that material is transported through the fluvial system and finds its way into often deep water sinks, sometimes alpine lakes for long periods of time. And so we have this idea about material moving from where the material is produced to where it is deposited, and that is the fundamental idea behind the source to sink idea. In order to better understand that source to sink concept, in geomorphology, we use mass continuity to understand how sediments are moved around in landscapes and how they are eroded. The law of conservation of mass states that the mass of a closed system will remain constant regardless of the processes acting inside the system. An equivalent statement is that matter changes form, but it cannot be created or destroyed. And so we can apply that concept in geomorphology. We can apply it to landscapes and write this very simple statement shown here. And that is that the input of a system to a particular landscape element minus the output of sediment from that landscape element will tell us what the change in storage of material within that landscape element is. And so when I say landscape element, it can really be anything. It can be a reach of a river. It can be a portion of a hill slope. It can be really a lot of different parts of the landscape. And so the fundamental concept here is that if you put sediment into a particular part of the landscape and you know how much sediment is leaving that part of the landscape, there's going to be some change in storage in that part of the landscape, and that's ultimately going to affect the elevation, which is what we're really interested in geomorphology, the elevation of the landscape. So these diagrams here show what happens in terms of elevation if you change the input and the output to a very simple landscape element. And so this landscape element here is basically just a box. So if the input of sediment is equal to the output of sediment from a landscape, we get essentially no change in storage. And therefore, the elevation, which is represented here by Z, is constant. However, if the input of sediment to a landscape element is greater than the output of sediment from that landscape element, then the change in storage of sediment within that landscape element has to change. It increases, and therefore the elevation of that landscape element will change, and it will increase. And so starting out with this condition again, where the input is equal to the output and there's no change in landscape elevation, you can envisage what happens if the input of sediment to a landscape element is less than the output. That changes the amount of sediment that is stored within that landscape element, and therefore the elevation must decrease. And so those two processes, the increase in elevation and decrease in elevation, are respectively deposition and erosion. It's useful in thinking about mass continuity concepts applied to landscapes to divide the landscapes into two general types. One is a soil mantled landscape. In a soil mantled landscape, it is one where we have weathered material that is stored on the landscape. And so the bedrock in this landscape is everywhere covered by soil. That is weathered material that builds up on the surface of the bedrock to a sufficient thickness to cover the bedrock everywhere. The contrasting condition, or the other extreme, is a bedrock landscape. That is one in which all of the weathered material is stripped from the landscape with no storage at all. And so then there is no soil built up in this landscape. So we have these two different types of contrasting landscapes. One is a soil mantled landscape, the other is a bedrock landscape. So we can write the conservation of mass or mass continuity equation for a soil covered landscape. And in order to do that, what we do is we set up very simple conditions, and we can then write the fundamental equations, making them more complicated as we move along through the derivation. So we're going to start out here. So this is another landscape element. And so in this landscape element, it's a little more complicated than the box I showed you before, in that it is a box, but it has two parts to it. The lower part of the box is made up of bedrock. The other part of the box on top is made up of soil or sediment. The soil has a thickness that we denote H. The elevation of the surface of the landscape we denote with Z. And then between the soil and sediment, there is a bedrock surface. And we need to pay attention to two things when we're thinking about the conservation of mass for a soil-covered landscape. One is, how does the separation, or how does that line between the soil and bedrock, how does it change through time? And then also, how does the landscape elevation change through time, which is what we're ultimately interested in as geomorphologists. So in this diagram I showed you right here, is that the change in landscape elevation with respect to time is zero. There is no processes introduced in this very simple diagram that would change either the bedrock surface position or the landscape elevation surface. And so for those of you who are not familiar with calculus, an equivalent statement to dz by dt being equal to zero is that delta z over delta t is equal to zero. That is, the change in the elevation with respect to time, or with respect to the change in time, is equal to zero. So we can begin adding some processes to this very simple situation right here, so we can derive equations that will predict how landscape elevation will change through time. And the first thing that we introduce here is soil production. And soil production is, at a very basic level, the conversion of bedrock to soil. The bedrock weathers and breaks down and is converted to smaller pieces that become ultimately soil or sediment. And so weathering ultimately produces a thicker soil profile. And so we've represented that here on this diagram by saying that the soil production rate, or P, is equal to the amount of converted bedrock divided by the change in time. And so we can write a very simple equation that represents the process that's happening in this diagram here, that says the change in elevation with respect to time, dz by dt, is equal to the change in the thickness of the soil profile, dh, with respect to time, dt, minus the soil production rate. Now, we're interested in how the landscape surface is going to change here. And the truth is, in this particular situation, the change in soil thickness with respect to time is exactly equal to the soil production rate, and what's happening beneath the landscape surface doesn't have much effect on what's happening to the surface of the landscape. What's happening at that bedrock interface is not affecting the surface of the landscape in this diagram I've shown here. Now, that's not always the case, because we can introduce other processes that unbalance that equation and make the change in landscape elevation with respect to time not zero. And so one of the things we can introduce here is the uplift rate of that very simple landscape element. And so the uplift rate is the amount of uplift we have with respect to time. And so then we can rewrite that equation and say the change in landscape elevation with respect to time is equal to the uplift rate plus the change in soil thickness with respect to time minus the soil production rate. We can make things even a little more complicated in that we can introduce deposition on the surface of the landscape. And so then in this particular situation, we have the change in landscape elevation with respect to time being equal to the uplift rate of the landscape plus the change in soil thickness with respect to time minus the soil production rate. And so in the previous slides I showed you, dH by dt minus P, the soil production rate, was always equal to 0. Well, that's not the case anymore here, because now we have two processes that are contributing to thickening of the soil layer. One is the conversion of rock to soil or sediment. That is the soil production that's happening. But then we also have deposition of material on the surface of the landscape. And both of those things are contributing to the thickening of the soil with respect to time. So we can then take that very simple equation that we derived there conceptually, which is the change in the change in landscape elevation with respect to time being equal to the uplift rate plus the change in soil thickness with respect to time minus the soil production rate. We can take that and we can try to make predictions of landscape elevation change through time. But the problem is that parameterizing that change in soil thickness through time is really hard if you don't specify the processes that are responsible for doing that. And so what we do is we take that variable, that change in the thickness of the soil, the change in soil thickness with respect to time, and we rewrite it. And we say that the change in the soil thickness with respect to time is equal to the soil production rate, that is the rate at which material is weathering, minus something called the sediment flux divergence. Now that concept of sediment flux divergence is really, really simple, but it might look a little complicated because the way I've written it here in this slide is as del dot QS. And that del dot QS, what it represents is the change in sediment flux across the landscape in 3 dimensions This concept of the divergence of sediment transport rate across landscapes, or sediment flux divergence, is really important in terms of trying to understand geomorphology. The change in sediment flux across landscapes tells us whether that landscape will change, whether that landscape will erode, or whether that landscape will deposit material. And so what I've done here to explain this concept is I've drawn a very simple landscape element. We have vertical elevation represented by Z here, and distance along the landscape represented by X. And we've drawn again a very simple landscape with some bedrock down here and then a little bit of soil sitting on top of it. And so we can think about what happens when the change in the sediment flux across the landscape is equal to 0. In that case, the amount of sediment that is going into this landscape element is the same as the amount of material going out of this landscape element, and therefore the net effect on the elevation of the landscape is 0. There will be no change in landscape elevation because the amount of material that is being transported across the landscape is not changing. If our sediment flux divergence, or our change in sediment flux across the landscape, is greater than 0, meaning that it is positive, we have a condition in which the sediment flux is increasing as it moves across a landscape element. And so therefore, we have a smaller input of sediment than we do an output of sediment. And so we go back to that simple concept I presented at the beginning of this video, where we have inputs and outputs and changes in storage in response to those. Here we find that an increase in sediment flux across the landscape creates a condition where we must erode the landscape, because we have less sediment going into the landscape element than we have going out of the landscape element. And that causes a change in storage that is negative, and that is erosion. We can consider the contrasting situation where the sediment flux divergence is less than 0 or negative. In this situation, we have sediment flux across the landscape element decreasing. That means that the amount of sediment that is moving into the landscape element exceeds the amount of sediment that is leaving the landscape element. Therefore, we have decreasing sediment flux across the landscape. And if that happens, we have a situation in which we must deposit material. And that's because if there is more material going into the landscape element than is leaving it, it has to leave that additional material behind, and it must then deposit that material. Now that we understand something about sediment flux divergence, we can write limiting conditions for different types of landscapes. And so if a landscape is completely covered by sediment, we can write an expression that tells us that the change in soil thickness with respect to time is equal to the soil production rate minus sediment flux divergence. And this is the sediment flux divergence, or the change in sediment flux across the landscape in 3 dimensions. This del dot QS is one term in this equation that will tell us about whether aspects of the landscape are eroding or depositing. So if we take that expression for soil thickness change and we insert it into this generalized continuity equation that we were deriving for the landscape a few slides ago, we can see that the change in landscape elevation with respect to time becomes equal to the uplift rate minus the sediment flux divergence. Now we arrive at this equation right here by taking this and inserting into the equation that we derived from our block diagrams a few minutes ago. And so this equation is interesting because one of the things that you'll notice is that the soil production rate disappears in this equation that describes landscape elevation change through time. And the reason why is because how much bedrock is converted to soil or sediment doesn't turn out to affect the landscape elevation, because there's no bedrock exposed at the surface. And when we have a situation like this, we refer to it as a transport limited landscape. A transport limited landscape is one where the amount of material removed from the landscape is not controlled by the supply of new material from beneath the landscape from bedrock. We can contrast that against a landscape that has bedrock exposed at the surface. There, the changes in the thickness of soil are directly related to the ability of flows at the surface to transport that material. And so in the thickness of the soil with respect to time, or the change in the soil thickness with respect to time, is equal to the sediment flux divergence, or the negative sediment flux divergence. And if we take that expression there and we insert it back into that generalized continuity equation we were trying to derive for the landscape, we get this expression here. And it tells us that the change in landscape elevation with respect to time is equal to the uplift rate of that landscape minus the soil production rate minus this soil flux divergence, or this sediment flux divergence, the change in sediment flux across the landscape in 3 dimensions. And here, the rate of landscape erosion becomes dependent on the rate at which bedrock is converted to either soil or sediment. And we refer to this as being a weathering limited landscape. that is where the amount of material removed from the landscape is ultimately controlled by weathering processes. So there is a third type of landscape that is important for us to understand. So if bedrock is exposed at the surface, the changes in the thickness of the soil are related to the transport rate. But if bedrock is exposed at the surface to flows, water flows, ice flows, or sediment flows, we modify our generalized continuity equation to include two things. One is the soil production rate, which was in the generalized continuity equation before, but we add another term in there, which is meant to represent the wear rate of the landscape. And so if we take this expression here and we insert it into the this new generalized continuity equation, what we wind up with is this expression down here at the bottom. And it tells us that the change in landscape elevation with respect to time is equal to the uplift of the landscape minus the erosion rate of the landscape, which includes both weathering processes and bedrock wear processes, right, where we have flows wearing away rock in the landscape, minus the sediment flux divergence. And there, the rate of landscape erosion becomes dependent on the rate at which bedrock is converted to soil or sediment, and the rate at which bedrock is worn down by flows, which in the past has been called corrasion and is still called corrasion sometimes now. So this is a different type of landscape. This is the landscape that is referred to as being detachment limited, right? That is where the amount of material removed from the landscape is ultimately controlled by weathering processes and by corrasion by flows or simple wearing away of the rock by flows. So that brings us to these three different types of landscapes, each one of which has its own version of the mass continuity equation. The first is a transport limited landscape, and that's where the amount of material removed from the landscape is not controlled by the supply of new material from bedrock below. We have weathering limited landscapes. That's where the amount of material removed from the landscape is controlled by weathering processes that break rock down, but that rock material is broken down in situ and is not transported away. And then we have detachment limited landscapes, and that's where the amount of material removed from the landscape is controlled by both weathering processes that break the rock down and leave it in place, but also by wear of bedrock or corrasion of bedrock by flows. So we have these three contrasting types of landscapes, all of which have different versions of that mass continuity equation. And so we can summarize those equations in this very simple statement here. It tells us that the change in landscape elevation with respect to time is equal to the uplift of the landscape minus the erosion rate of the landscape or a bedrock in the landscape minus the sediment flux divergence or the change in sediment flux across the landscape. And so this leads us to try to understand geomorphic transport laws. So in order to make predictions of landscape change, geomorphologists need to parameterize those variables here, or those terms, including the bedrock erosion rate and the sediment flux divergence. And that bedrock erosion rate is represented here as E, and it includes sediment production by weathering processes that are happening at the bedrock soil interface and by bedrock erosion by glaciers, wind, and sediment embedded in water flows that actually wear away the bedrock. And then we also have to understand this sediment flux divergence, which tells us whether the sediment that sits at the That's a bit of a mouthful. We also have to understand the sediment flux divergence, which tells us whether the sediment sitting at the surface of the landscape is going to be eroded or deposited. And the primary erosion and deposition processes are mass wasting processes, that is, hill slope processes such as landslides and debris flows, and fluvial transport processes, which are the processes that move sediment through river systems.